We are recording. We're looking at that problem that we just talked about when you left class, writing equilibrium expressions. Noticing that these are all gases, so they're all included. The equilibrium expression would be K equals products over reactants. The products are NH3. I apologize for the sloppy writing. Squared. Again, that's concentration. I should do that better, not the parentheses. Over N2 to the first power, because he just has a 1 in front of him on the balanced equation, and H2 to the third power. And that's it. That's the K expression. Now for B it gets a little bit trickier, and the only tricky thing for B is the fact that he's a liquid, so he's not included. Again, I've got two products, so K is going to equal products over reactants. I'll draw this line so we know that that's where A stops. My products are HCO3 minus bicarbonate ion, concentration to the first power because there's only one of them, and H3O plus, which is an acid. We'll talk more about that H3O plus being an acid in our next unit. And the one reactant that we have that's aqueous or a gas, and that's H2CO3. Again, water is not included because it is so pure it has a concentration of 100%. It doesn't have to be included in KC expression. And again, I might want to write that all these are KC expressions so that I don't later on get confused. Ignore that line. Okay, for C, gets even a little trickier because I've got a solid on both sides. This is a single replacement reaction. Hopefully you can see solid C is replacing A, and then you're ending with BC. So K is going to equal, again, I'm only going to include aqueous solutions, products over reactants. The only product involved is BC. Again, this is more of a generic form. BC is not a real thing. And the reactant that is aqueous, AB. The solids are not included, the same reason water's not. That's pure. There's no concentration to it. It's a solid. So moving on to the next part of K expressions. You should be able to look at a reaction and its K value and predict whether it's reactant or product favored. Now, again, if we go back and take a look at what we wrote down here, if K is greater than 1, the reaction is product favored. If K is less than 1, the reaction is reactant favored. So when I look at these K values, because he's less than 1, this is a product favored reaction. All right, it's less than 1. That number is much less than 1. It's 12.120, and 12 zeros, 15. You know, a very, very, very small number, meaning that barely any of this complex ion turns into copper and ammonia. Where down here, it still is reactant favored because it's still less than 1. It's not nearly as less than 1, but that's, more than a millionth. Basically, that's saying is that if we had 10 million samples of this, nearly all of them would stay over here, and maybe 2 would turn into, 2 of the 10 million would turn into a cadmium ion and an NH3. It's heavily reactant favored. It's just some of them turn into ions. Now where that can get tricky to understand, and I've got a diagram of this on this next page here. If I wrote the equilibrium expression for both of them, both reactions look very similar. But again, it's saying for every one CuNH3,4 I have, for every one reactant, I have 1.5 times 10 to the negative 13 products. Meaning that's a very, 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 very small number of these products per every one reactant I have. Same thing's true down here. Now if I look at both of these though, to try and answer this question, if each reactant above has a reactant concentration of 0.1 molar. So we start out with 0.1 molar of him and 0.1 molar of him, which solution is the NH3 concentration greater? Now we did say that they both are product favored. Again, this is product favored, and this is product, or excuse me, We did not say they're product favored. We said they are reactant favored. Talk about the products in a second. This is reactant favored, and this is reactant favored. But what this question is really asking us is who's more reactant favored. And now if I look at this number, he is much more reactant favored, meaning more stay as reactants in this example than in this example. This number, again, if we wrote it out on the screen or on the board, or you write it out on your own, it's 0.00000001. Very, very small. But if we write this number out, it's 0.00000000000015. Much, much, much smaller. Not twice as small. Way bigger than twice as small. Twice as small would be if it was 0.5 times 10 to the minus 7. This is like a magnitude of 1 billion times smaller. Much, much smaller. Maybe not quite 1 billion, but really small. So what that tells us, answering this question, is if I have 0.1 molar of him and 0.1 molar of him, this has to be larger for this guy, because even though he's reactant favored, he's much less reactant favored than this guy. This guy is extremely reactant favored because he has such a small K. He is very reactant favored, but we're going to see more products formed for him. So which solution is the NH3 concentration the greater? It would be greater in the cadmium ammonium ion solution, because his K value is closer to 1. It's not very close to 1, but in comparison to this guy, it's much closer. So again, the closer you are to that value of 1, the closer you are to a 50-50 split. Above 1, more products than reactants. Less than 1, more reactants than products. So moving along, looking at what else we didn't cover. I think this is where we are. Yep. So you can see, we said that we can solve for Q, and somebody had asked about this in class, are we ever going to have to find Q? And the answer is yes. We can solve for Q at any conditions. If we solve for Q, again, a Q expression and a K expression look exactly the same. One's just at equilibrium, K, and one's not, Q. If Q ends up being less than the equilibrium constant, K, the system is not at equilibrium, and some of the reactants will be converted to products. That means that we haven't quite reached the stage we need to, and more reactants still need to react to get our K higher. Where if Q is greater than K, Q is too high. We overshot the reaction, and some of the products will have to be converted back into reactants. When Q equals K, the system is at equilibrium. And again, you can see page 664, the butane versus isobutane equilibrium graph. Iso is just talking about isomers. We're going to talk about isomers later on, but basically think of it, this is one thing. Isobutane is the same formula, just different set of bonds. And again, you can look at that and read the caption in that graph to help you out understand what's going on. Last thing then, if we have that, we should be able to now calculate for Q. So I'm going to write out what the Q expression is for this particular situation. Q would equal, and it equals the same thing K does, products over reactants, NO squared, because it's NO, 2 NOs, over the product, or the reactants, N2, and the concentration of O2. Well, because we don't know if this is at equilibrium, but we are given values. So we can go ahead and plug these values in and solve for Q. So Q is going to equal, we know what K is. It tells us the K value. Somebody already solved that for us. Remember, K has no units. But now I can find with these concentrations, what would this be? I have 4.2 times 10 to the minus third squared. That would be the NO concentration. 4.2 times 10 to the minus 3 squared, because it's the NO concentration, over the N2 concentration, 0.5. I'm doing a really bad thing right now, and I am not using my units. I should be using my units, but we'll see that since we square this one, they will cancel with these down here. You should be using your units right now. Shame on me. And 0.25 for the concentration of O2. Now, when I type that in on my calculator, as it says over here, Q equals 1.4. Well, if we compared that to our K, up here, 4.0 times 10 to the minus 4, 1.4 times 10 to the minus 4, Q is less than K. So the reaction is not at equilibrium yet. And what it's saying is that right now, the ratio between the products and the reactants is less than it should be. It's a smaller number than it should be. So to fix that, we're going to have to add more products, and when we add more products, we're obviously going to remove some reactants until it gets to that equilibrium. So we know this reaction will proceed to the right, or in other words, it's going to make more products. Hopefully you do your reading. Tomorrow we're going to talk about a very important concept, these ice tables, and we'll be using these ice tables. So again, do your reading. Make sure you completely understand day one, because it's truly the foundation for the next month of our course. Hopefully you enjoyed our time together. I know I sound, well, I guess to you guys I don't sound funny recorded, because that's what I always sound like, but whenever I listen to myself recorded, I always think it sounds funny.